Hi, calculus students. Today we're talking about 2.3 differentiation rules, part 1, basic differentiation rules and rates of change. In this section, you will learn some rules for finding derivatives. This will help you avoid having to use the limit process. Before deriving some of the rules, here's a list of ways that you can represent the derivative and assume that all of these functions are y as a function of x. So if you look across the top, you've got f of x, and then you have f prime of x. F prime is the derivative. dy dx, that's the Leibniz notation. And this middle one is the derivative, taking the derivative with respect to x of the function x. So it's really an operator. This is the derivative with respect to x of y, and then y prime is, of course, very common. So the first thing we're going to do when we're talking about differentiation, we're going to talk about the proof of why f prime is equal to 0 for a constant function when f of x is equal to c. So if we set this up, we've got f prime is equal to the limit as h approaches 0 of f of x plus h minus f of h, minus f of x over h. And then since it's a constant function, if we want to prove this, what we're going to do is we're just going to realize, all right, if it's f of x is equal to c, it's always c. So when I put the c in here, when the input is x plus h, when the input is x, it's still going to be c. So c minus c is 0, and I've got to just fix one little adjustment here because we've got a limit involved here. The limit as h approaches 0 of c minus c, which is equal to, and I'm going to write this down here, the limit as h approaches 0 of 0 over h, which is equal to 0, the limit as h approaches 0 of 0, which is equal to 0, the limit of a constant, and it is, of course, a constant. So therefore, the derivative of a constant is 0. Now, then if we consider the function f of x is equal to x, then f prime is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So then remember now, if you input x plus h, you're going to output x plus h here. So you get x plus h, and then f of x is equal to x. And so then when you subtract it, you get the limit as h approaches 0 of h over h, which is equal to the limit as h approaches 0 of 1, which is 1. So we have the limit, or f prime is equal to 1 when f of x is equal to x. So there are a few others of these that we worked on, and remember, it's kind of important that you get very comfortable with this idea. Take the limit as h approaches 0 of f of x plus h minus f of x all over h. So recall that when you are doing these, see if you can just play around with these a whole lot, getting a high level of comfort. But what you want to do is just make sure that you understand the process, that it's not that difficult once you engage with the process. It just is one of those things where you just need a little practice. So remember, you can cancel the x squareds there, factor out an h, cancel. So now remember, you want h to go to 0, so what you're going to get is 2x plus 0 here, which is just 2x. Okay? All right, for the next one, then recall that you're going to be using Pascal's triangle when you want to multiply x plus h, the quantity cubed, or you just memorize that it's going to be x cubed plus 3x squared h plus 3x h squared plus h cubed, and then we're going to minus x cubed, and then that's all over h. And so remember, the x cubes are going to cancel, and you get the limit as h approaches 0. H approaches 0 of, we're going to factor an h out, giving us 3x squared plus 3xh plus h squared, and then that will simply be over h. Cancel the h's, and then you get the limit as h approaches 0 of 3x. Actually, we could just go ahead and take the limit then. I mean, if you like. and just plug in 0 for h. So that's equal to 3x squared, and which we know to be true using the power rule. Okay. All right, moving on. So we have these rules, some basic differentiation rules. We have the constant rule, the power rule. We have a power rule where we bring the exponent around front and then we drop the degree of the exponent by 1. We have a constant multiple rule. So if you see this constant here, then you can take the constant and move it in front of the derivative here. And then just take the derivative of x, which is f prime. We have the sum, and that's called the constant multiple rule. And then we have the sum and difference rule, where if we can just go left and right and take the derivative of each term in a sum or a difference. So here we go. Using the rules just presented, find the derivatives of the following functions. So one of the things we do is we do a lot of rewriting, but in this first one, we have a constant, and what we can do when we have the constant multiple rule, we can just leave that 3 right there and then go ahead and take the derivative by using the power rule. So you can see that here we get f prime of x is then equal to, let's equal down a little bit, is then equal to 12x to the third power. And there you have it. Okay. Here we want to rewrite the expression because we need it in one of these forms where we're able to take the derivative, and we want to write it as a power. So I'm going to write this as y prime then for the derivative is equal to, now I have it as the power rule, so that's what I'm going to use. I have it in that form. So then I'm going to bring the exponent around front. So remember my n is equal to -1 here. And then I have x to the -1 minus 1. So that's going to be equal to -1x to the -2nd power. But we can write that a little bit neater. We can say, all right, well, I'm going to write this as negative, and I'm going to put the 1 up top, and I'm going to bring the x to the -2 down to the denominator as x squared. And there you have it. There you go. Okay. All right, then we have g of x is x cubed minus 3x squared plus 2x plus 7. So we have this rule that just says we can go from term to term and take the derivatives. So we would get g prime of x is equal to the derivative of x cubed, which is 3x squared, minus the derivative of 3x squared, which is 6x, and then plus the derivative of 2x, which is 2, plus the derivative of 7, which is 0. So you can see that plus 0, that's not going to be anything, so this will be our answer, g prime. Okay, then we have h is equal to 1 over 3x squared. Now, the 3 in the denominator is just 1/3, 1 over 3, but the x to the second power in the denominator is x to the -2, so we can write that in that power form. So I get h prime is equal to, then I'm going to bring the -2 out front. Let me change the order of these just to stick with the rule. I'm going to leave my constant out front, and then I'm going to use the power rule. I'm going to use the power rule on x to the -2. So then I have h prime of x is equal to -2/3, and then it's going to be h to the -3rd, but we are slightly more comfortable with writing this as -2 over 3x cubed. And there you have it. Okay. All right, so there's that. Now we're going to practice a few of these rewriting. Why don't you pause your video and give it a shot, where in each of these there's going to be a slight little rewrite before we go ahead and take the derivative. Okay. All right, now that you're back, we're going to use a dy dx notation, Leibniz notation for this. And then I'm going to say 1/2 x to the 1/2 minus 1/2 minus 1, and then plus 3. The derivative of 3x is 3. And then we have dy dx is equal to, so this is going to be 1/2 x to the negative 1/2 plus 3. And we could write that, I'm going to just fit it in right here, where this is going to be 1/2 square roots of x plus 3. And I just box that up right there. Now we could write that as one fraction if we wanted to. It would be 1 plus 6 square roots of x all over 2 square roots of x, but we're good there. All right, for this next one, when we want to do the derivative, so we're going to multiply this together, expand the x minus 2, And so once we get x squared minus 4x plus 4 as our k of x, we're just going to take the derivative, which is 2x minus 4. And there you have it. Hope that worked for you for those two. And let's move on. So now with the next one, we've got a fraction where we've got a polynomial over a monomial. So we can rewrite that. We could do a couple different things. We could have multiplied the numerator by x to the negative 2. But what I did instead is I just took the denominator and I rewrote each of the terms of the numerator over that denominator. And now I'm going to simplify. So I get y is equal to 1 minus 2x to the negative first power plus x to the negative second power. And now I'm ready to take the derivative. dy dx is then equal to, it's the derivative of 1 is 0. So I'm just going to leave that out. And then I have the derivative of the second term is then going to be 2x to the negative second power, and then it's going to be minus 2x to the negative third power. So that's going to simplify nicely as 2 over x squared minus 2 over x cubed. And there you have it. There it is. Okay. And then for this last one, or the last rewrite, we have f prime of x is equal to 1/2 times x to the negative 1/2 power minus, then I'm going to have this plus 3/2 x to the negative 3/2 power. So remember, you're subtracting 1 from these exponents. So 1 negative 1/2 minus 1 is going to be negative 3/2. So we have f prime of x is equal to 1 over 2 square roots of x, and then over here we have plus 3 over 2 times x to the 3/2. Now, there are different ways to simplify, and sometimes there's little return on your investment, but there are times where you definitely want to simplify. Right now, I'm going to leave that as our answer. Okay, then we have write the equation of the tangent line to the function y is equal to 2x squared plus 1 over x squared. So the first thing I do is I think about beginning with the end in mind. And so I want to get the equation for the line. So I know I want to write the equation of the tangent line to the function at the point 1, 3. So I have the point slope form for that all set up. And I know that y prime is equal to the slope of the tangent line at that point. That's what I need for y prime, or the slope that I'm going to put in there. So I say y is equal to 2x squared plus x to the negative 2. So a real quick rewrite, and then I have y prime is equal to 4x minus 2x to the negative third power. So you're lowering the power when you're taking the derivative. So we have y prime, and we want it at, see, it's y prime is a function of x. So all I need to do in that is use we want the slope at this point, so I'm only looking at the x value on the point. So I have y prime of 1 is equal to 4 minus 2, which is 2. And then I'll come up and put this in. I get y minus 3 is equal to 2 times x minus 1. And I'll write that in point slope form as such. 3 plus 2 times x minus 1. There you have it. There's the equation of the tangent line to the graph of the function y is equal to 2x squared plus 1 over x squared at the point 1, 3. And then we have different ways that we can calculate. If it says at what points, we have algebra that we can use for this next problem, or we could use calculus. If you see the algebra method is that if you want to find the point on the graph that will have a horizontal tangent line, you're thinking, all right, it's either going to go like this or like this with a quadratic, and you're thinking, okay, the horizontal tangent line has to be at the vertex. So either the vertex is going to be a minimum value, such as the one I just wrote on, or it's going to be a maximum value. So either way, we look at this one and we say, well, A is less than 0. So we're talking about that graph. So we can use the algebra 2 method. It's a little longer. When you take the derivative and you find that the slope is 4 minus 2x as a function, and you want to know where does it have a horizontal tangent, well, the horizontal tangent occurs when f prime is equal to 0. So once you get the derivative, set it equal to 0, then you're just going to solve for x. So you get when x is equal to 2. So at what points, just at one point, so it's really a points and s with the parentheses around. So at what point, so now we need to plug back in and get f of 2. F of 2 is equal to 4 times 2 minus 2 squared. So it's going to be 8 minus 4, or 4. And then the area problem, the area of a square whose length is, for this one, that's going to be 2, 4 is the point where you have the vertex of the graph where f prime is equal to 0. One more, and it should polish off this lesson. The area of a square whose length is given by a is equal to s squared. And at what rate is the area changing when s is equal to 2 or when s is equal to 5? So the derivative is a rate of change. And so what rate is the area changing when s is 2? So you take your area formula, which is equal to s squared, and you take the derivative. So it's going to be just 2s. And then you plug in 2 for s. So when the side is 2, 2 times 2, and that's equal to 4. Now, notice I'm keeping some units out right now. For this a of 5, it's going to be 2 times 5, or it's going to be 10. So you see that when the side goes up, the rate increases significantly. So if the side was 10 units, then you could see that, well, then it's going to be 2 times 10, or 20, for the rate of change. So I want to kind of hold off on talking about the units, but remember, area is units squared over the side, which is units. So when you divide that, the units is really going to be the length. So it would be something like inches for a prime, because it's units squared over units. But we'll talk more about that. So that's it for today's lesson, and I will see you when I see you. Have a great day.